All right. Hello, everyone. My name's Leaf Jiang, CEO of Nodar. We're based out of Boston and also Berlin. And I've had quite a journey going through automotive markets before ending up in ag. I never thought I'd be talking at FIRA. But it turns out that a lot of the problems that we see out in autonomy are pretty much universal. And our company focuses on software, namely ultra-wide stereo vision software for doing advanced 3D perception for robots in difficult environments. And so we've released a software called AgriView for robots to be able to see in dusty environments, to see in bad weather, and be able to make perception decisions accurately. All right, and so because it's sort of a general purpose, where we live in the stack is from the camera end, so very, very much at digitizing the world up into creating 3D point clouds of the surrounding environment, all the way up to creating occupancy maps. And that's where we live in the space, which is fairly generic and is the general problem that all these agricultural robots you see here today have to solve. And so we've worked on a number of problems in ag, not just for tractor autonomy, but also for sprayer alignment, for swath following, for precision instrumentation and being able to put things where you need them to be. And so what we offer is a pretty simple system design. AgriView consists of basically 2 cameras and a computer. It doesn't really get simpler than that. What's new here is this ultra-wide baseline stereo vision. And so stereo vision's an old technology. It's been around for a long time, but being able to see at distances that matter for agriculture have been hard to do until you can take these cameras, and they basically work like human vision. You're triangulating distances and having a larger baseline or a larger distance between them. So now you can see, instead of 5 meters ahead, you can see out to actually hundreds of meters ahead. These 2 cameras generate 3D point clouds that go to an embedded computer, and there's where all the software magic happens that's used to then servo the rest of the vehicle. Here's a quick diagram of the different software blocks in our system. The enabling technology here is really the calibration, the ability to know where the cameras are in space, because you are measuring angles with stereo vision. Any sort of perturbation, even as small as 1/100th of a degree, can ruin your measurement. And so our core IP is around being able to do that calibration quickly per frame, accurately to sub-pixel registration, and also on natural scenes, because we can't have engineers running around with checkerboards. And so seeing out to longer ranges is important for ag. You typically don't need to see highway speeds, so you don't need to go hundreds of meters. But typically 50 meters and above is important for improving the safety margin of your system. One of the key things that's holding back autonomy, and the reason why we can't go out and buy tractors today and they haven't taken over the world, is because they simply have productivity issues. The mean time between interventions is now typically 1 to 2 hours before someone needs to go out and hit a reset button. And that is a problem that needs to be unlocked. That's the problem that we address. We can see farther and more accurately. This allows us to reduce the false alarms, especially in important edge cases. That allows us to reduce both the MTBI, or mean time between interventions, as well as increase the probability of detection for safety. Seeing farther helps us close that sort of safety margin. Here's an example of our system running in a field actually in India. This is a field where you have off-road, you've got a left camera shown, a depth map, and the point cloud. These are 2 cameras that are placed about a meter apart, 5.4 megapixel images, processing in real time on an NVIDIA Jetson hardware, so embedded SoCs, very efficient processing, generating a very, very accurate reconstruction of the surroundings. And the power here is not just that you have the location everything, which is XYZ, but you have XYZ RGB, and that's important for not just knowing where things are, but what things are. So the color channel can be used for what's called semantic segmentation, or understanding the surroundings. Is that point a person, or is that point a fly, basically, or something that you shouldn't stop for? And so we've done this over and over again in different places. This is in the Midwest. This is comparing our system against 128 channel LiDAR, showing the enhanced range and the ability to see things in higher resolution. This allows a number of things to be done, from being able to follow very small swaths to really understanding where the ground is to be able to actuate the tractor correctly. The right-hand side is our system. It's a color depth map. The left-hand side is the LiDAR. And so this is an example of what that raw data looks like coming out of the system. Again, another application. Here's a nighttime application of a combine harvester. There's a spout that's operating, a grain spout that's operating at night, which is the second image from the left, showing that we can, even in low light conditions, reconstruct the point cloud very accurately. We can see where the grain's going in the grain cart, and the whole thing is done with just simply cameras in this case. There's nothing fancy here. These are standard, in this case, 2 megapixel cameras. This software operates with any cameras. They don't have to be horizontal. They could be different optics even. So it's a general solution. We've done a lot of testing in dust. We've done testing from low dust to heavy dust. This is probably too much detail. The big takeaway here is that compared to LiDAR, we see about 2 to 3 times more points, or we have 2 to 3 times more penetration. And this is important for, obviously, agricultural applications. We've done a lot of testing in adverse weather. This was done in an automotive test facility with fog and rain and different levels. Again, very similar, fog and rain. These are distributed scatterers. For cameras, this shows up as reduced contrast. That's the physical thing, and again, that's why you end up with like this 2 to 3 times improvement versus LiDAR. And so one of the things that's really important for building these systems is redundancy, and this is redundancy not just by having more and more sensors, which, as you've heard from the previous talks, growers can't afford. So getting redundancy in your perception, that is in your software, by using both the XYZ and the RGB channel is something that we do, so we can look at the 3D structures and determine what's in our way. We don't need to train on it because we never have to have seen that particular object before with 3D. And then we have the classical sort of AI approach of using neural networks to see what objects are there and combine those 2 channels for redundancy to be able to drive or actuate these vehicles reliably. And so here's another example of our system running in yet another field. So this is in California. Upper left is the video image of the left camera. There's also a right camera, 1.2 meter baseline, 5 megapixel imagers. The upper right is the bird's eye view of the point cloud, which shows 5 very well distinct objects there, different kind of targets that were placed there, from mannequins to cones to different things. And the point cloud on the bottom. All of this is generated just using cameras. And when you have such high quality input, it makes the driving decisions a lot easier and the ability to detect a lot easier. And so, again, we've repeated this. This is an experiment we did in Germany, swath following application, where we went to the customer, plugged in our system, and they were driving autonomously within 2 hours, following swaths out to 50 meters and 10 centimeters high. So super fast swath following here. An example of a video showing that. The right-hand side is the bird's eye view of that swath. If you look at the image, you can't even see where the swath is because it's a dirt swath here. It was at the end of the season. And so being able to pick up the 3D structure is often easier than just trying to recognize it from the image. So we can get to a point where actually we're exceeding the capabilities of the human driver and perception, being able to see farther through fog, being able to see more subtle structures than a human could pick up. And so we're in a new regime here. Even on the camera side, they're more sensitive than human eyes. They have higher dynamic range than human eyes. And you can obviously set the optics to have better resolution. Okay. So, so that's it. I guess, this is AgriView. We're Nodar. We do wide baseline stereo vision perception software, applying it to several applications within the agricultural space. We also have worked in automotive and mining, which has similar issues with dust. But yeah, pleasure talking here today.
Okay, let's thank Leaf. Any questions for Leaf? Yes.
Hey, I'm Lucas. I'm a student at the University of Hawaii, and I was just curious. I'm actually a ROS2 programmer, and was wondering if you guys use ROS2 as your control integration, I guess.
For sure. So ROS2 is like the language of robotics. So we have a ROS2 API. It's at ros2.nodarsensor.net. If you go there, you'll have our ROS2 API. We also have an API for ZMQ, and those are the two APIs we have.
That's cool. I actually have one more question, if that's okay. I was curious how you guys actually, I guess it's kind of answered by the first question. I was wondering how you guys translate the data that you receive and translate that into like an actual control mechanism for the teleoperation of the robots.
Yeah, so that's where we hand off to the OEM. So they want to control that part. That might have. So we have up to the fusion layer something called grid detect that takes in the stereo channel. It could take in LiDAR or whatever, and then give you an occupancy map. And then we pass that occupancy map to the path planner. So there's a lot of open source path planner algorithms, and then that would go to actuation and stuff. All that typically is owned by the OEM. Okay. Yeah.
Very interesting. Thank you.
Thanks. More questions? Anybody? Question? Yes.
So is it, so my name is Harpreet, I'm from Dallas, Texas. So we have a strawberry farm, and it's a small operation. So are you getting to enterprises or small farmers or the mid-size? I know you're in multiple industries, farming is one of them. So what's the cost of, you said you did this implementation in 2 hours for one of your customers.
Mm-hmm.
If I was to work with you and say, hey, I have my like 50, 70, 75 horsepower small tractor, what does it take for you to do it for me? And do you even work with small farmers?
Thank you. I didn't talk about our business model. So we're a software company, and when I say customers, I usually mean like OEMs that we work with, because we don't have the full solution. We don't sell tractors, and we don't sell the complete solution. We do the perception part. And so you would work with, I guess, one of the OEMs that we would work with to implement on your strawberry farm. But yeah, I think this is a big project to solve, right? And it's done by multiple people to bring a real product that you can service over time. And so that's currently our business model. So I don't think we plan on building and selling tractors anytime soon. There's a lot of great ones here already.
Okay, good. There's time for a couple more questions. Questions? Anything coming to mind? Any questions from anybody?
Okay.
Okay, thank you so much.